Okay, this is the first lesson in part 2 of Unit 1 for trigonometry. And in this part of the unit, we are introducing oblique triangles. An oblique is just another name for non-right triangles. As a point of note, when we label non-right triangles, we tend to use capital letters A, B, and C to represent angle measures, and lowercase letters A, B, and C representing side lengths. And since there is no 90-degree angle, there's no need to specifically label angle C as the 90-degree angle. So C can be any angle measure in a problem. Now, to remind you, when the instructions say to solve a triangle, let's remember that that means to find all side lengths and angle measures. So your results for this problem might differ depending on how you label your triangle. Now, typically what I do is I label the angle A in the uppermost position of the triangle, and then I move counterclockwise around the rest of the triangle. So if I place angle A in the top, I'm going to place angle B in the bottom left, and then angle C. So that gives me this counterclockwise rotation. And then we can identify side lengths fairly easily as well. Side length A is across from angle A. Side length B is across from angle B, and side length C is across from angle C. Now, 3 of the components out of 6 are going to be supplied to us. In this case, there are 2 side lengths and 1 angle measure that are provided. Sorry, I said that backwards. 2 angle measures and 1 side length that are provided. So solving for the third angle measure is quite easy. The sum of these 3 must be 180 degrees. And if 90 degrees is associated with the angle C and 45 for angle B, then it stands to reason that angle A is also 45 degrees. Many of you will recognize that if angle A is 45 degrees while angle B is 45 degrees also, then side length A must be 16 units in length. Because with two 45-degree angles inside of a right triangle, we're talking about an isosceles right triangle. And an isosceles triangle requires that 2 non-right angles are congruent, and the associated side lengths with them are also congruent. So side length A is equivalent to side length B. So finding side length C, we've got a couple different options here. We can use right triangle trigonometry with sine, cosine, or tangent, or we can use the Pythagorean equation. We haven't used the Pythagorean equation lately, so I'll go ahead and use it here. Recall that the Pythagorean equation states that the sum of the squares of a right triangle's side lengths is equal to the length of the hypotenuse squared. So a squared plus b squared equals c squared. So it stands to reason that 16 squared plus 16 squared is equal to c squared. So then 512 is equal to c squared after we sum together 16 squared twice. And after we apply the square root to both sides of the equation, we'll note that c by itself is equal to 22.6274 units. Now, clearly, the square root symbol in an algebraic sense does produce both a positive and a negative result here, but we're not interested in the negative result, of course, because the length of a side cannot be negative. So we will report the final side length as 22.6274. And while 3 components were given and 3 components were unknown, we were able to solve for the 3 unknown, and we have a solution for all 6 components of this triangle. Now, with right triangles, the methods for solving them is pretty straightforward. I mean, we have sine, cosine, and tangent in the form of SOHCAHTOA. And as we saw in this last example, we've also got the Pythagorean equation that can be used as well. So when solving for a missing side length or angle measure, those 2 techniques work just fine in right triangles. Unfortunately, for oblique or non-right triangles, this notion of SOHCAHTOA isn't nearly as helpful. So for our new concept, what we're going to note is that there are four different cases, if you will, of non-right triangles. And these phrases should look familiar to you had you taken a geometry class prior to this, where the letters A and S stand for the words angle and side. We can describe a triangle as an angle-side-angle triangle or angle-angle-side triangle. In this case, if a triangle is composed of two angles and one side length, we consider that a case 1 style triangle, or a triangle that falls into case number 1. When we're supplied two sides and an angle measure that's not included in between those two sides, we consider that case number 2. When two side lengths are provided, but an angle in between those two side lengths is provided, we call that case number 3. And when three side lengths are provided in an unknown triangle, we call that case number 4. What you'll notice is that there is no case for angle, angle, angle. If 3 of the 6 components to a triangle are provided, and all 3 of those are angle measures, then it's impossible to identify the unique or precise triangle that fits that criteria. In fact, there's an infinite number of triangles that meet the criteria if only 3 angles are provided. For example, this triangle might meet the criteria if 3 angles are provided, 3 unique angles are provided, but another triangle, slightly larger, could also have the exact same angle measures, but it would not be the same triangle as before or as prior. So with 3 angle measures specified, there's no way to know precisely which triangle we're trying to describe. There's no uniqueness applied to the angle, angle, angle triangle. So as long as one side length is provided in an unknown triangle, along with the other remaining components, we can solve for a specific and unique oblique triangle. What I would like for you to note at this point is that oblique triangles that follow case 1 and 2 will be solved using what we call the law of sines, and we'll introduce that in just a moment. The law of sines is used for case 1 and case 2, while the law of cosines is going to be used for cases 3 and 4. And before we introduce the law of sines and the law of cosines, let's quickly decide which case is applied or associated with each of these triangles. Now in this unknown triangle here, if I'm being asked to solve it, that means to find angle C, side length A, and side length B, I would do so by using the appropriate law, either law of sines or law of cosines. In this particular case, an angle measure an angle measure A and an angle measure B with a side length in between is provided. So this is what we would consider an angle side angle triangle, and this is associated with case number 1. Therefore, we would use the law of sines to solve it. In this example on the left, we have a side length, 2 side lengths, and an angle measure in between. Therefore, this is an SAS triangle, and we would be using the law of cosines because this is case number 3. In this example here, we have 2 side lengths, 12 and 12, and an angle that is not included in between. So this is an SSA triangle, which falls under case number 2, and we would use the law of sines to solve this triangle. In this example here, we have the letter X that represents an unknown value. My recommendation there is when you see the letter X, just ignore it, cover it up, or erase it if possible. Because before you can solve for X, you have to identify which type of triangle that is presented to you. In this case, we have a side length 8 and a side length of 2 with an angle measure provided in between. Therefore, this is an SAS triangle, which falls under case 3, and we would use the law of cosines to solve this particular example. Take a look at these 3 or 4 examples over here on the right-hand side and pause the video now to determine the type of triangle and case number associated with it. Resume playback in a moment to check your work. And these are the types of triangles that are introduced along with the case numbers associated with them. If you continue to have trouble identifying the types of triangles associated with these diagrams, please make sure that you reach out to me via email or a message through Schoology, or ask for help next time we see each other in class. Now, the law of sines and law of cosines are as follows. The law of sines states that the side lengths of the sides are proportional to the sines of the corresponding opposite angles. And that phrase by itself may be a bit confusing or intimidating, but if we look at the equation associated with it in this block here, you ought to be able to memorize this. Sine of A divided by A is equal to sine of B divided by B, which is also equal to sine of C divided by C. We often call fractions proportions, so that's where the phrase proportional comes from. And while angle A is noted with the capital letter A, the side length opposite of that is lowercase letter a. And so sine of one angle measure and its opposite side length, B, in this middle case, and angle C and side length C, correspond with one another and are all equal. The proportions are equal. With the law of cosines, which is a bit more wordy, the square of one side of a triangle is equal to the sum of the squares of the other sides and the opposite of twice the product of the other side lengths and the cosine of the opposite angles. So again, that phrase is quite a bit more wordy than the law of sines. And if we were to look at the law of cosines by itself, again, there are some patterns here, and you ought to be able to memorize or at least recognize the behavior of these equations. Now, oftentimes, textbooks will provide the law of cosines in a single form. In fact, it'll look something like this third example, or iteration number 3. If I continue to erase other components of this law of cosines, you might notice that this law of cosines in its third iteration is exactly the same as the Pythagorean equation, and that's exactly true. The Pythagorean equation is literally an extension of the law of cosines. So the Pythagorean equation is just an extension of the law of cosines, and it's a specific example of the law of cosines where where angle measure C is equal to 90 degrees. Now, the other two forms of the law of cosines are essentially the same as this third form here. They are forms of the Pythagorean equation. In each case, we account for the nature of non-right angles inside of the oblique triangle. And there are some specific patterns with the layout of each of these equations. You'll note that side length A on the left-hand side requires angle measure A on the right-hand side. Side length B on the left will require angle B on the right, and side length C will require angle C on the right-hand side. You should also notice that the two side lengths, b squared and c squared, in form number 1, are used, b and c, inside the component that multiplies by the cosine of angle A. Side lengths a and c in the second form are used again in the product that multiplies by cosine of b, etc. So there are some patterns here that are established, and if you can memorize just one of these forms of the law of cosines, you can modify that form in order to fit the requirements of any other oblique triangle that fits this criteria. So let's finish out this video with two examples. In example number 1, we have a satellite that's orbiting Earth, and it passes directly overhead observation stations in Phoenix and Los Angeles. Now, the distance between Phoenix and Los Angeles is 340 miles. At this particular instant, when the satellite is between these two stations, its angle of elevation is observed to be 60 degrees above Phoenix and 75 degrees above Los Angeles. So if I recreate this diagram in a simplified view with just the triangle provided, you should note that two angle measures with the side length in between is an ASA triangle, which falls under case number 1, is going to require the law of sines to solve. In this particular application, we're not going to solve the entire triangle. The question only asks, how far is the satellite from Los Angeles? So when we're talking about the satellite and its distance from Los Angeles, we are talking about the side length along this diagonal of the triangle. Now, you can see in the provided image, as well as in this diagram, the side length that we're searching for is side length B. So the law of sines says something like this: sine of angle A divided by side length A is equivalent to sine of angle B divided by side length B, which is equal to sine of angle C divided by side length C. Now, I don't know that this component of the law is going to be all that helpful to us. What I do notice is that angle measure B is provided, so we can calculate sine of 60 degrees. We don't know side length B. That's exactly what we're solving for. We at the moment don't know what angle measure C is, but that's going to be easy to obtain. We can see that in just a moment. And we also recognize that side length C is 340 units in length. I said that angle measure C is easy to compute because we have two of the three angles within the triangle known. And the third angle measure is easy to obtain because we can subtract that from, 180 degrees. So that's going to leave us with a angle measure here of 45 degrees. And now we can use our calculator to solve. Sine, when evaluated at 60 degrees, is 3 pi divided by, the square root of 3 divided by 2, or 0.8660. Sine of 45 degrees is the square root of 2 divided by 2, or 0.7071. We'll divide that by 340. Now, anytime that I've got two fractions that are equivalent to one another, I should recognize that the cross products are also equivalent. And we could multiply across the diagonals, divide by the third component that's not a part of the known diagonals, and the end result after that series of steps will always be the fourth unknown value in the proportion. So off screen I've calculated 340 times 0.8660 divided by 0.7071, and the end result that I obtained for side length B is 416.4050, and the units in this particular case is going to be miles. So evidently the satellite is 416 miles from Los Angeles. We can complete a similar example. As we see here, a tunnel is to be built through a mountain, and to estimate the length of the tunnel, a surveyor makes the measurements shown in this figure below, and we will use the surveyor's data to approximate the length of the tunnel. Now, in this particular diagram, the side length that's unknown here is angle measure C. We're provided with one side length, a second side length, and an angle in between. So I would call this an SAS triangle, which is case number 3. And with case number 3, we are going to use the law of cosines. Now, the law of cosines at first looks an awful lot like the Pythagorean equation. And in this case, I'm looking for side length C. So I'm going to choose the third option, option number 3, or form number 3 of the law of cosines. And that's the one that states that C squared is equal to side length A squared plus B squared. And I've memorized this, and I suggest that you do the same. So I know that the next step is going to be minus 2 times AB, the same two side lengths that are provided here on the right side. And I'll have to multiply by cosine of angle measure C. In this case, angle measure C, side lengths A and B are provided. The only unknown is side length C. Now, before I start substituting values in, I might notice that if I'm solving for side length C, this lowercase letter c, then I could take the square root of both sides of the equation and isolate side length C, or lowercase letter c, in one step. So that's what I'm going to do here. Lowercase letter c is equal to the square root of a squared. A squared is 212 squared, plus b squared. Now b is 388, minus 2 times 212 times 388 times cosine of angle C. Now angle C was provided at 82.4 degrees. If I take the square root of this total result, then I'll obtain the result and correct distance for side length C. And I can enter this in a calculator in one step, and that's what I'm going to do off screen right now. And after entering this expression in the calculator, I obtain 416.8096, and that measurement is a distance in feet. So evidently the tunnel through the mountain has to be approximately 417 feet in length. Hope you found this particular video interesting as an introduction to the law of sines and law of cosines. In the next video, I'm going to provide several triangles for you to work with, and you must identify the cases for each triangle, and ultimately I'll ask you to solve them. So please download a blank copy of the notes from Schoology and begin the process of identifying these. When provided a diagram, such as these examples 3 through 12 on the left-hand side, identifying the cases isn't too difficult. However, when provided elements of a triangle without a diagram, it can be a bit more challenging. So my recommendation for you is, when a diagram is not provided, then simply sketch a plain or a simple diagram to determine your cases. If you draw some arbitrarily shaped triangle with side length A, B, and C, along with angle measure A, B, and C, you can mark that diagram with the provided information. For example, in number 13, we know that angle A is provided as 50 degrees, and angle B is provided as 68 degrees, while side length C is 230 units. Now, the diagram may not be drawn accurately, but at least we can clearly see that this is an angle side angle triangle. And when solving problem number 13 from the left-hand side, since it's an ASA triangle, we would use the law of sines to finish solving it. So there's a little trick while looking ahead at the next assignment in this week. And I would ask that you take the time to practice that before you watch the next video. Thanks for watching.